everyone, and thanks for having me here. So, as it was introduced, my talk will be about capacity of phase-sensitive preamplified receivers, which is a work that I've done together with Antek, Mikos Nuszkiewicz, and Radim Filip. So, I will begin by giving you a brief introduction to communication theory. So, in a general communication setup, you have incoming signal that is quantified by the average number of photons per slot. This signal goes then through a noise channel that adds some noise. And then it goes to a receiver, which is basically a device that transforms your quantum states to classical variables that encode a message. And there are many different quantities that you can come up here to characterize the performance of such a setup. But the most obvious one is called capacity, which is just the maximum amount of information that can be transmitted per single slot. And now you may think about two different regimes here. So if you look at classical literature, so in classical literature there are no photons, you have only electric field, then you may find that the bound on the capacity is given by this formula. This is known as Shannon-Hartley bound. And as I told you, there are no photons, everything works on the level of electric fields here. So this basically assumes that everything is Gaussian. So you have Gaussian modulation of coherent states, and you perform homodyne detection of a single field quadrature. And a nice feature about this formula is that the signal and noise enter it only through the ratio. Yeah? So you have signal in the numerator, and in the denominator you have total noise. Yeah? So this 1/2 here is not some arbitrary factor. It's basically the shot noise of your homodyne detection. So you just take into account the total signal-to-noise ratio. On the other hand, we know that there is something more than homodyne detection in nature. So you may optimize this capacity over all possible conceivable physical measurements that in principle include collective measurements, very complicated things. And then if you do this, you may come up with something which is called Gordon-Holevo limit, which is given by this very complicated formula. But there are two important things about this equation. First of all, is that it doesn't include detection noise, because you take into account the optimized measurement. So the optimal measurement is not noisy. And also, there is something more to it than just the signal-to-noise ratio. Yeah? So you see here that signal and noise enter this equation independently. So that's the basics. And now let's switch our focus to a particular example. So I will be talking about the deep space communication. So deep space is basically everything that lies beyond the orbit of Moon. So let's say I have a satellite that flies around Mars and it wants to send a message down to Earth. So it sends a laser pulse, which is received by an optical telescope. And these are some parameters for this setup, which are given here, well, rather generously. So like in practice, you will not have 12 meters telescope. Yeah, it's rather more like 2 or 3 meters. But what is important here is that the received power is proportional to the squared ratio of the receiver telescope diameter and the beam diameter. And now, due to the extreme distance of Mars and Earth, which is 56 million kilometers at the very closest approach, this beam will be the beam diameter will be of the order of hundreds of kilometers. Yeah, which means that this fraction here, this factor, will be very small. So the received power will be much smaller than the power at the transmitter, which basically means that this communication link will operate in what is known as photon-starved regime, which is characterized by the average number of photons per slot much smaller than 1. Yeah? So there are examples of optical communication links where the average number of photons is like 0.01. And this is a very interesting regime for communication, because in the plot of the capacity, we are basically interested in this regime here. Yeah. So you see that all the curves are very close to each other. So capacity is not the best quantity to visualize the results here. It's usually much better to use what is known as photon information efficiency, which is basically just the capacity divided by the signal strength. And this gives you just the amount of bits that can be encoded in a single photon. Now, if you look at this photon information efficiency, you may find that for Shannon bound, for the Shannon-Hartley limit, so for the classical case, there's an ultimate limit, which is just 2.88 bits per photon or 0.33 photon per bit, depending on the units that you want to use. And you cannot beat this by any means if you are stuck with homodyne detection. And on the other hand, this Gordon level bound in this the photon information efficiency for the Gordon level bound is unrestricted. Yeah, it can grow to infinity. Yeah? So in principle, there is much to fight for here. So it's good, it's promising. But also, if you add noise, then well, it's not so beautiful anymore because noise destroys this advantage. So you can still gain something above the Shannon bound, but well, you'll not reach this infinity. So the question right now is how to fight with this noise. So if this noise enters your setup at the detection stage, so it's the detection noise, then an obvious answer is to simply amplify your signal. Yeah? So there are two types of amplifiers. The conventional one is phase-sensitive amplification. So such devices basically amplify your signal with some factor at the cost of adding some noise. And this noise, unfortunately, is proportional to the gain. So that's not good, because this means that we are fighting one type of noise with adding another type of noise. So we don't want this. So we can consider phase-sensitive amplification. So a phase-sensitive amplifier amplifies only one quadrature of light at the cost of de-amplifying the other one. But the nice thing about it is that this is in principle noiseless. Yeah? So basically the transformation is just squeezing. Yeah? So this is unitary transformation. So we would like to have this kind of behavior. And yeah, you may consider phase-sensitive preamplification. So the first thing that you can investigate is how the homodyne detection would change if you add this preamplification. Yeah, so how the Shannon bound will enhance. And this was actually done recently, yeah, a few years ago. And this is the result that was obtained. So there was even an experiment about this. And you see here that this device, this PSA preamplified homodyne detector, is good when you have around 1 photon per slot signal strength. And basically, it's the best thing you can come up with from known measurements. But in this very low photon number regime, where, for example, Psych emission that demonstrated optical communication from deep space last year operates, it's, well, not very good, yeah, because you hit this 2.88 bits per photon limit. But you see, if you look at this plot, you see that there is this green curve that outperforms this PSA. So you may ask, okay, what is this green curve? Yeah, it outperforms even this amplified detection. And this is just direct detection without any amplification. So you may ask, okay, so what will happen if we add this PSA amplifier to direct detection? And this is exactly what we considered. So we considered imperfect direct detection. So we have photon number resolving measurement here with some non-unit detection efficiency, with some additive noise and possible channel losses. And we added the phase-sensitive preamplifier. And to be general, we considered displaced squeeze states for our modulation. We optimized over all possible modulation schemes using some very clever classical algorithms. And these are the results. So in the ideal case, when you have no losses, no noise, there are 3 conclusions that you can take from these results. So first of all, amplification helps for direct detection. Yeah, so those curves go up. Secondly, it doesn't help for homodyne detection. Yeah, so you see that it's pointless for homodyne detection if you have ideal case, if you have no noise. And the third case, and the first conclusion is that, well, homodyne detection is much better than direct detection. Yeah, so the gap is almost like 30 or 40%. And also interesting thing here is that for this ideal case, without losses, without noise, it's beneficial to use squeezing. So you really want to have this squeezed ensemble because this allows you to enhance the capacity by above around 30%, at least for homodyne detection, but also for this direct detection. Okay, so that's bad because this homodyne detection seems to be very good, at least for this larger number of photons. So what happens when we add noise here? And when we add noise, there are like two obvious conclusions. So first of all, squeezing does not help. Yeah, so those dashed curves are almost the same as solid ones. And that's obvious because if you have losses in your channel, then squeezing is destroyed. So why there is no point on spending your energy on squeezing. But secondly, you see that the curves for direct detection approach the curves for homodyne detection. Yeah? So that's promising, yeah, because it seems that there is something to this amplified amplified direct detection receiver if you have noise. And you may also look at this problem from a slightly more practical point of view. So in practice, usually you want to have large bandwidth. And it's very difficult to have homodyne detectors with very large bandwidth, which is not the case for direct detection. So in fact, for this larger number of photons, it may be so that you may be able only to get homodyne detection with very limited efficiency, whereas it's not the case for direct detections. You may have still the advantage, which comes from just the fact that the efficiencies are different here. Okay, but let's look at this photon start regime, because I told you that this is more interesting, yeah, because there will be possibly there will be advantage there. And well, in fact, if you look closely at this plot, maybe you can see that those curves for direct detection are slightly above, but it's barely visible here. So yeah, let's look in this for this enhancement in this very low signal strength regime. And yeah, if you plot the photon information efficiency, this is what you get. So the main take-home message from here is that indeed this amplification really helps both for direct detection and for homodyne, yeah, because it can grow your PIE by a factor of 2, even if your gain is 3, and also that it's really beneficial to have direct detection than homodyne detection. So this is promising for those deep space missions, because this means that you can enhance your capacity just by adding this phase-sensitive amplifier before your detector, and you can fight noise. You don't need to do anything really more complicated. Although maybe phase-sensitive amplification is not very straightforward, but yeah, that's the main take-home message. That is very beneficial. So the conclusions are that phase-sensitive amplification at the receiver allows to minimize the impact of detection inefficiency and noise. It's also very well suited to direct detection in photon start regime. And if you think about possible ways to go from these results, you may look at practical modulation formats, so on-off keying or pulse position modulations, which are actual formats used in deep space missions, or for short haul links where squeezing helps. So there are low losses, so it may be also beneficial to use this PSA there. And with this, I'd like to thank you.
Questions, please. Don't see any. I may have missed it. So do you assume for this deep space communication, do you assume you have coherent signals?
Sorry?
Do you assume that you have coherent signals?
Yes.
So your signal is, yeah. So I was just wondering if this is, can you comment on how realistic it is to get a coherent signal over this many million kilometers?
Well, coherent signal, I mean, you send coherent states, yeah? But, since you are using direct detection, yeah, then you are not really interested about the phase, yeah, because you're just encoding your information in the amplitude or the photon number, yeah. So, like the phase coherence is not crucial here, yeah. So it's just that we usually use coherent states because they are easy to work with, yeah. But I guess if you use just standard like thermal light with different number of photons, it should work. Yeah.
Okay.
Yeah, thank you. Did you also have a look at probabilistic amplifiers? So not phase sensitive, but
No.
Okay.
No, it was already very difficult to calculate all these things, because like the probability distribution for this phase sensitive amplified detection receiver, it's really complicated. So there are like papers from 90s where they calculated this distribution. It includes like infinite sums. Yeah, so the crucial point is that you need to take a cutoff somewhere, and this cutoff depends on the strength of your signal. So if you have amplification, the energy of your signal grows. So this cutoff will grow like, I don't know, like 1,000 or even more. Yeah. So it was already very difficult to do this, numerically at least.
Okay, I think we cut off. Thank you very much.